Let's continue with our lecture on invertible matrices. So previously we said that if a matrix A is invertible, then if we have the equation AX equal to B, we can find its solution by simply multiplying on the left by the inverse. And then we can see that A inverse times A is the identity, and that the identity times any vector x will just give us x. I just want to make note of some things that you cannot do with the matrix inverse. For example, if I have AX equal to B, I cannot say A times X times A inverse is equal to B times A inverse. This presents a problem because B is n by 1, and A inverse should be n by n if A is n by n, so we cannot perform this product. Another thing that we cannot do is to insert A inverse on the inside of AX, right? This is also something that is not legal. And lastly, we never want to solve this system by doing the following. AX equal to B means that we divide both sides of the equation by the matrix A, which gives us B over A, which is equal to A inverse B. Right? This is illegal because this would assume that A inverse is 1 over A, which is not true for matrices. As part of this theorem, I'm going to verify that x equal to A inverse B is actually a solution to AX equal to B. To do that, we do the same thing that we do in algebra, and that is we substitute into our matrix equation our solution for x. So we get A times A inverse times B should give us B on the right-hand side. We can reorder the way that we take the product, so we can do A times A inverse times B equal to B. And then A times A inverse gives us I times B. And of course, we know if we were to take the product of the identity matrix with any vector, we get the vector back, which shows that we have an equality. So this is actually a proof of the theorem because first, we took our original equation, AX equal to B, and we showed that the solution is x equal to A inverse B. And then we took the solution, x equal to A inverse B, and we substituted it back into our matrix equation to verify that it is indeed a solution. So that shows that the solution is unique. Here are a few properties of matrix inverses. The first one states that A inverse itself is an invertible matrix, and when we find the inverse of A inverse, we end up with A. The second one says that if A is invertible, its transpose is invertible. And it doesn't matter whether or not we take the transpose first and then find the inverse, or find the inverse and then find the transpose, we'll end up with the same result. The last one seems a little bit counterintuitive, and that is that if I take the product of two matrices and find the inverse, it is not equal to A inverse B inverse, but in fact it is equal to B inverse A inverse. And we're actually going to prove this on the next slide. The theorem states if A and B are both invertible matrices, then the product of A and B is invertible, and the inverse of AB is B inverse A inverse. So to actually prove this, we must show that if we multiply by the inverse on both the right and the left, so it's not just enough to show that multiplying it on one side, you get the identity. You must show that when you multiply it on both sides, you get the identity. So let's start. So we're going to take the matrix AB, and we're going to multiply by the inverse on the right. So that's AB inverse. So we get A, B, and now let's substitute in what AB inverse is. It's B inverse A inverse. Now we can reorder our product in the following way. So it's A times B inverse times A inverse, which gives us A, B times B inverse. Again, B is invertible, and if I multiply it by its inverse, I get I. And then I can take the product of I with A inverse. So the identity, of course, multiplied by any matrix or vector will give that matrix or vector back. So this is A times A inverse. And of course, since A is invertible and I'm multiplying it by its inverse, I get the identity. So I've shown that by taking the product of the inverse on the right, I get the identity. Now I must do the same thing by taking the product on the left. So here is the result of multiplying by the inverse on the left. Again, I just made a substitution of B inverse, A inverse on the left-hand side. Then I did some reordering, found that I got the identity. Then I have B inverse B, which again gives me I. Since when I multiply AB by the inverse on the right and on the left yields the identity matrix, then we can conclude that AB is invertible and that its inverse is AB inverse equal to B inverse A inverse. So I'd like for you to actually try to do this by assuming that the inverse is A inverse B inverse, and you'll see that this result does not work. We're about to make a connection between elementary row operations and the matrix inverse. And so to do that, we have to introduce this idea of the elementary matrix. An elementary matrix is simply a matrix that is obtained by performing one and only one row operation on the identity. So we're going to look at an example where we're dealing with the 3 by 3 identity, which we have right here, I3. So let's look at E1. So to get to E1, we must perform one row operation on the identity. It turns out that E1 represents a row interchange, because to get E1, we take the identity and we do an interchange of row 2 with row 3. So again, this elementary matrix represents an interchange. E2 represents a row replacement. To get E2 from the identity, we have to take row 1 and replace it with 2 times row 3 plus row 1. So again, E2 represents a row replacement. And lastly, for E3, this is a row scaling because we've taken row 2 and multiplied it by 3 times row 2, and so this again represents a row scaling. Something very interesting happens when you take a matrix, let's say this matrix A that we have here, and you multiply it by some elementary matrix on the left. So here we're going to take the product of E1 with A. So just recall that E1 represented an interchange of rows 2 and 3. So I would like for you at this time to pause the slide and actually perform the product for yourself. You should have obtained the following matrix. Notice that what has happened to A is that row 2 and row 3 have been interchanged. So when we multiply by the elementary matrix E1, which was an elementary matrix in which an interchange had been done on the identity, we end up performing that elementary row operation on the matrix A itself. Let's go a step further and multiply the result of E1 times A, which is given by this, by the elementary matrix E3. So if you recall, E3 was resulted from a scaling of the second row of the identity by 3. So now we're going to multiply E1A by E3 on the left. And if you perform that product, you'll see that what happens to that result is that the second row is scaled by 3. So all the elements are multiplied by 3. So notice when I multiply a matrix by an elementary matrix on the left, it simply performs that row operation on the matrix. So I could have a succession of such row operations. Let's say EK dot 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 E3, E2, all multiplied by A, and that would simply perform all those row operations that are identified by each of these elementary matrices on the matrix A. You recall the way that we find elementary matrices is to perform one row operation on the identity to get the elementary matrix. To find the inverse of an elementary matrix, by the way, all elementary matrices are invertible. To find the inverse, we simply find the row operation that transforms the elementary matrix to the identity, and we perform that operation on the identity to get the inverse. So let's look, for example, at E1. To get E1 back to the identity, so we want E1 going to the identity matrix. For that to happen, we again have to do a interchange of rows 2 and 3. If we perform that row operation on the identity, we get the inverse. So E1 inverse is 1, 0, 0, 0, 1, 0, 0, 0, 1. So notice that, oh, I'm sorry, we have an error here. Again, it's an interchange of rows 2 and 3, so that should be 0, 1, 0. Oops, sorry. I'm supposed to be doing this on the identity. I'm doing it on the wrong matrix. So we get 0, 0, 1, 0, 1, 0. Again, we perform row 2, an interchange of rows 2 and 3 on the identity to get the inverse. Notice that E1 is its own inverse. So E1 inverse is equal to E1. So at this point you should pause the slide and perform the multiplication of E1 with E1 inverse on both the left and right to verify that it is indeed the inverse. Now let's see how we find the inverse for E2. So to go from E2 to the identity, we have to perform the row operation that row 1 goes to minus 2 row 3 plus row 1. So if we perform this row operation on the identity, we get the inverse. So E2 inverse is 1, 0, negative 2, 0, 1, 0, 0, 0, 1. Again, you want to verify that E2 is inverse is the correct one by multiplying it both on the left and right of E2 to show that you get the identity. Just in case it's unclear, let's go step by step through the process for finding E2 inverse for the matrix E2, right, the elementary matrix E2. So again, we first want to know what row operation was performed on E2 or needs to be performed on E2 to get to the identity. And we found that that row operation was that row 1 has to be minus 2 row 3 plus row 1 because that will help us eliminate that 2 and make it into the 0 that we need for the identity. So to get the inverse, we then take the identity matrix, which is given here, and we perform that row operation on the identity. So we want to perform this on the identity matrix. And what we get, again, we do negative 2 times row 3 plus row 1, and we end up with the following matrix, which again is the inverse of E2. So now that you understand the process, I would like for you to try to find E3 inverse on your own. The result should be the following. Again, to verify that E3 inverse is the inverse of E3, you must multiply it on the left and the right of E3 and show that you get the identity. The theorem that you see right here is extremely powerful, and it's powerful because it actually tells us how to find the inverse of any n by n matrix. So the theorem says the following. If I have a matrix that is invertible, first of all, it means that it is row equivalent to the identity matrix. So an invertible matrix is row equivalent to the identity. And then the next part tells us how we actually find the inverse. It says that the sequence of elementary row operations that reduces A to I transforms I to A inverse. So what does that mean? Let's say that I create an augmented matrix that has A on one side, and I augment it not with a B, but rather the identity. And then let's say I perform row operations on this and put A into reduced row echelon form. So again, it says that A is row equivalent to the identity. That means once it is in reduced row echelon form, it will become I. And then it says those same row operations. So notice that when I'm performing row operations, I'm performing them equally on A and on I. So this theorem says that those row operations that transformed A to the identity are again going to transform the identity to the inverse of A. So what you should end up with on the right-hand side of this augmented matrix will be the inverse of A. So we're not going to prove this theorem at this point, but we are about to make use of this theorem to find the inverse of several matrices. Let's use our theorem to find the inverse of this 2 by 2 matrix. So according to the theorem, I need to set up the augmented matrix that contains A on the left and the 2 by 2 identity on the right, perform row operations on A until I get the identity, and the identity is going to transform to the inverse. All right, so let's start the process. So on the left-hand side, I'm going to put the matrix A, and on the right-hand side, I'll put the 2 by 2 identity. And now I'm simply going to perform row operations to try to make A the identity matrix. So for the first one, I'm going to take row 2 and transform that to -3 row 1 plus row 2. And that is so that I can make this element 3 into a 0. So if we perform that row operation, row 1 does not change. So I just rewrite row 1, and row 2 becomes 0, -1, -3, and 1. Alright, so now I'm going to perform the row operation to make this element 2 a 0. And so I need to do another replacement. That will be row 1 goes to 2 row 2 plus row 1. So in this case, row 2 does not change, so I have 0, -1, -3, and 1. And row 1 becomes 1, 0, -5, and 2. Alright, so I'm almost done. I just have to change one more element. This -1 needs to be a +1. So I'll perform the row operation, which is a scaling of row 2. So row 2 is going to go to minus row 2. So row 1 does not change, so it's 1, 0, -5, 2. Alright, so let me make this correction. It looks a little messy. So again, that is -5, 2. And row 2 becomes 0, 1, 3, -1. So notice that what I have, again, I finished because now A is equal to the identity. So on the left I have the identity, and on the right I have the inverse of A. So we know that A inverse is equal to -5, 2, 3, -1. And hopefully you'll notice that this is exactly the same result that we got previously for the same matrix when we used the formula for 2 by 2 matrices to find its inverse.